We are Team Agni. In response to challenge number 2, developing a small, lightweight UAV system with autonomous navigation, we are designing, building, and programming a lightweight UAV system to aid emergency rescue searches and procedures. There are various problems current emergency response teams face today. Such problems include constantly changing dangerous environments, unknown variables, slow response time, reduced visibility in fire and smoke, and the fact that they have no idea where stranded victims may be. Though they are often successful in their missions, such factors pose risks that can make missteps potentially fatal. But what if we could eliminate the unknown, reduce response time, and help emergency rescue teams locate victims? Team Agni seeks to solve this problem with a pathfinding drone. On this slide, we have a rough sketch in which you see an example of what the drone would look like. The drone will use SLAM, a 3D mapping software, to map out the environment and allow the drone to self-navigate to the designated destination. Once there, with the help of a visual light and infrared camera, the drone will be able to detect heat and analyze the buildings surrounding to help aid rescue teams.
Our project will utilize a 3D mapping technique called SLAM. SLAM stands for Simultaneous Localization and Mapping, and we will use it to map out the general vicinity. As the drone flies through a city, weaving its way to the location of the supposed fire, it will look at its surroundings with a camera and use the visual input to create a 3D map. It creates a 3D map by analyzing the tiny differences in objects' locations as the camera pans and rotates. It is similar to using parallax to find the distance of faraway stars. SLAM can also account for non-permanent objects such as birds and cars. However, if the cars are stationary, they will be included in the resulting output. The output of SLAM is a 3D map in the form of a point cloud, which is a digital representation of the 3D world. To help you understand what point cloud means, imagine seeing a wall as a gigantic array of dots. The essence of SLAM is that it locks onto the position of points that it denotes as key points, and then it compares new points to those key points. That is the reason why SLAM returns a point cloud. Using a thermal camera in conjunction with the normal camera will allow us to set the temperatures of points in the 3D map, allowing to understand the fire in a more detailed way. This level of detail will provide firefighters with a deeper understanding of a fire's location and spread. Over time, as more and more calls are answered, the 3D map will expand in size to hopefully cover most, if not all, of the city that the drones operate in. Another aspect is that multiple drones can be in the air at one time simultaneously, and the camera feeds from all the drones will be sent back to a central server. The central server will be running SLAM and will be controlling the drones using pathfinding algorithms that rely on the 3D map. SLAM, with a bit of tweaking, will be able to process multiple inputs at once. The most important part, however, about SLAM is that it features loop closure. What loop closure is the ability to recognize a place that the drone has been before, connecting new data with old data, and fixing old paths. Fixing old paths means that it will make sure the entire map is scaled correctly and that there aren't any warped places. This is especially important because pathfinding algorithms would not be able to function otherwise. Other mapping techniques would provide a map as well, but those maps would have a similar form as a long, winding snake. This means that if it mapped a circle, and if you wanted to go from where the path ended back to the start, you would have to backtrack your entire way. With SLAM, however, the end and start of that circle would be connected, and the circle would exist as one continuous entity, allowing for the pathfinding algorithm to directly take the shortest path, or understand that the end of the circle path was the beginning. This also means that if we were to map a square with SLAM, the end result would have an accurate square that was continuous and the size would be the same length after SLAM accounted for odometry drift. After we have the map, another algorithm will translate the digital 3D map into an analog map using filters that turn recognizable patterns into surfaces labeled as grass, road, wall, etc. We can then effectively use a 3D map with a pathfinding algorithm to create more efficient flight paths and have a more thorough understanding of the building and road layout of future calls. The surfacing algorithm will also allow firefighters more information on where utilities could be set up and could be used in partnership with map software such as Google Maps. During the firefighting, SLAM could also be used with another memory algorithm that mapped the building as the fire progressed. This would give firefighters a video of the building as the fire raged so they can analyze how the building structure failed during the fire in order to improve future missions.
From the moment our drone begins flight, it will stream its visual camera feed to a central server, which will run the SLAM algorithm and map out the surrounding area. Since SLAM only maps the environment and does not tell us how to navigate it, we use an A-star search algorithm to direct the drone around obstacles. A-star supplements the Dijkstra search algorithm with additional heuristics, guiding the search efforts toward the end goal more quickly. From any starting point, the A-star algorithm creates a list of all possible movements it can make from that point while avoiding obstacles. For each movement, it uses the heuristic to assign two scores. One represents how close to the goal it is, another represents how difficult it is to make that movement. Based off these two scores, the algorithm selects the most optimal step of movement. Then it repeats the process by adding possible moves from the current point into the list of all possible moves. By combining the two heuristic scores, the search algorithm is guided toward the end goal and always avoids obstacles in the way. Once it reaches the end point, the algorithm returns the path it took, which is always the most optimal path. The point cloud generated by SLAM will be used to determine whether or not a movement will collide with an obstacle. The drone will always stay a certain distance away from those objects, which can be adjusted at any time. Additionally, the infrared camera will be used to avoid excessive temperatures. Although SLAM will not function properly on infrared data, as the camera is not of high enough resolution or contrast, each point generated by SLAM is associated with a temperature from the infrared data. Using a perspective transformation to project each of the new SLAM points onto the surface of the infrared camera, the temperature is directly sampled from the two-dimensional camera feed and assigned to each new SLAM point. This will create a 3D temperature map of the entire building and surrounding area. Using the temperature map, we modified a heuristic of the A-star algorithm to avoid areas of excessive temperatures, which could damage the drone, allowing it to avoid both obstacles and heat as it moves quickly toward any destination. In artificial intelligence, we utilize the SLAM and A-star algorithms to control the flight of the drone. By default, it will continuously fly around the targeted building in order to provide emergency responders with a real-time map of the entire area. The flight path will be generated from the A-star algorithm, and perpetual motion will keep the SLAM up to date on the environment. If necessary, however, the drone can be manually overridden by a human controller and flown to any area of interest, allowing for synchronization of the drone's efforts with the efforts of the firefighters on the ground. To further assist their efforts, visual camera, infrared camera, and 3D map of the building will be readily available to firefighters in order to provide as much information about the environment as possible in a clear and easily understandable way, optimizing their ability to rescue victims and extinguish the fire.
To recap, the benefits that Agni offers is a fast response time as our drones can fly directly to the site of emergency, thus being able to avoid all traffic along the way. Using SLAM to map the environment around it and using A-star algorithm to find the optimal path around obstacles, the drone will be able to avoid any hindrances along its way. This enables the drone to navigate in a sophisticated manner and get to the objective as efficiently as possible. Agni constantly provides rescue workers with an update on the situation while they are arriving. With the data collected from the drone, the operator can tell the rescue teams where potential victims are and what to expect, where to go when they arrive at the scene. Lastly, Agni will be incorporating current technology to aid rescue workers in quicker, more efficient search and rescue of victims.
And now we come to a close. While we have thoroughly discussed our idea and methods we intend to use to solve a real-life problem using unmanned aerial vehicles, the one important question that remains is cost. Here at Team Agni, we realize that no matter how useful or amazing an idea is, the real determining factor of its potential development is how much money it takes to realize the goal. With that being said, we will now break down our projected price. Our drones will be 3D printed using carbon fiber filament to increase durability. The drone, as mentioned before, will also have an infrared camera and regular visual camera. The remaining cost is attributed to miscellaneous electrical parts, including motors, wires, and batteries. Together, for a cheap prototype, a single drone will cost around $300. If a 3D printer were also to be included, it may vary the price from an additional $200 or potentially a couple thousand, depending on the quality of the printer. If this project were realized, mass production could drop drone prices dramatically, providing cheap but useful equipment to help save lives.
Thank you for your time.